Let's solve problem 2 from a textbook. Given two particles with charge Q1 and Q2, and they are initially separated by distance, given distance, and then they brought closer together to the final distances, 1.5. What is the change in electric potential energy? This is very straightforward problem. Just have to apply formula we just learned. Just write it down. Given Q1, 45 microcoulomb, Q2, 85 microcoulomb, R initial, 2.5 meters, R final, 1.5 meters. Change delta in potential energy is question mark. So how we would approach it? Change in potential energy is equal potential energy final minus potential energy initial into charges K, Q1, Q2 over R final, not squared, just plain R final, minus K, Q1, Q2, R initial. Let's simplify it. K, Q1, Q2, 1 over R final minus R initial. And after we plug in all the values, I'm not going to write it here. You can look at the solution that I posted online. We're going to get the value 9.2 units. What are the units here? Joules, of course. This is energy. That's it. Now let's solve problem 6 from a textbook. We're given electric dipole that consists of charges plus Q and negative Q, as sketched on this figure. And the question is how much work is required to place a charge Q at the origin. Assume Q starts from very far away. How we would solve this problem? We have to apply principle of superposition. Initially, Q was far away. What does it mean? That means R is equal infinity. That means if we divide something by R, where R is infinity, that is practically 0. That means that potential energy initial was 0. Now, let's find final potential energy. Potential energy final is going to be consisting of two parts. The first is potential energy between these two particles. We can write it as K, negative Q, little q over L, plus potential energy, electric energy between those two particles. I use blue color. So it's K plus Q times little q over L. Let's rewrite it this way. Negative K Q Q over L plus K Q Q over L. We're getting 0 again. So final potential energy is 0. What we can say about work? Work is equal from initial to final delta potential energy, and it's going to be equal 0. There is no work being done in this situation. Why is it 0? Well, this is simply means that when we're bringing charge from far, far away, we have to balance forces from negative charge and positive charge. From negative, just highlighter, from negative Q to positive Q. And one of those forces is attractive and a second force is repulsive. So those forces are balanced each other out, and so sum of all forces becomes 0. So no work is done by bringing charge from infinity to center of electric dipole. Now let's solve problem 9. This will be the last problem for this part. We are given 3-point charges and that arranged the way how it's shown in the figure. What is the total potential energy of the system? How we go about that? Like with these problems, let's make the slide small over here, then I can work on the side. Okay, here we are. Givens. Q1, 2.5 microcoulombs. Let's just write it down for you. It's 10 to the negative 6 coulombs. Q2 is equal 4.5 microcoulombs. Q3 is equal negative 3.5 microcoulombs as well. And the distance are L and 2 L's, but L is 1.5 meters. Question is, find total potential energy, electric, of the system. So how we do that? We have 3 charges, and we have to apply formula for potential energy between 2 charges 3 times. So potential energy, electric, is equal K, Q1, Q2 over distance. Let's write it R1, 2. This is between first and second, plus K, Q1, Q3, divided by distance between 1 and 3, plus K, Q2, Q3, divided by distance, R2, 3. Okay, what are those distances? R1, 2 is the distance between first charge over here and second charge over here. So this is going to be L, and the distance over here is Pythagorean theorem. So it's radical L squared plus L squared. It is L radical 2. It's easy to simplify. So let's look R1, 3. 1, 3, where we have 1 over here and 3 over here. So we have 1 and 3. This is distance L. This is 2L. Pythagorean theorem again. It's just L squared plus 2L squared is equal L radical of 5. R2, 3. Distance between those 2 charges is easier. This is just 3L. Okay, now we can plug in numbers. We can factor out K. Just rewrite it. Q1, Q2 over L radical 2 plus Q1, Q3 radical 5 over L plus Q2, Q3 radical, no radicals here, just 3L. So I can factor out L, right? I'll just use magic of eraser. Where's my eraser? Here's my eraser. Okay, we would erase, oops, just L, L, L. I factor it out. Just correct what we had here. Oops, erased wrong part. Factor out L, so just 3 here. Okay, that's what it is. Now we can plug in numbers. 9, 10 to the 9. L is 1.5. And please do it by yourself. Be careful with the sign. Plug in here values for Q's. And after you calculate it all, what we will get? We would get from answers, hopefully it's okay, 7.2, 10 to the 3 joules for energy. Don't forget, for microcoulombs you have to use 10 to the minus 6. And that's pretty much it. So we're done with this part of the lecture.